So, dear students, so far we have seen the conceptual framework and also the problem ones. It may be the easiest chapter if and only if anybody knows the vectors very clear in concept. So, mathematically, vector உடைய concepts ரொம்ப clear தெரிஞ்சிருந்தா இந்த chapterல problem போட முடியும். Problems வந்து ஏன் எந்த விதமான எக்ஸ்பிளனேஷன் இல்லாம கண்டினியூஸா ரன் பண்ணோம் அப்படின்னாக்க மோர் ஆர் லெஸ் ரேஷியோ ப்ராப்ளம்ஸும் டைரக்ஷனல் ப்ராப்ளம்ஸும் வந்துருக்கிறத பார்க்கலாம். இப்ப கான்செப்டை நல்லா கிளியர் பண்ணிக்கலாம். அதுக்கு பிறகு ப்ராப்ளம் ஏரியா போனாக்க ரொம்ப அழகா புரியும். ஸோ இப்ப நான் முதல் பார்ட் ஆஃப் த கரண்ட் எலக்ட்ரிசிட்டிய, அது மேக்னெட்டிக் எஃபெக்ட் ஆஃப் கரண்ட்டை, ஒரு கரண்ட் ஒரு கண்டக்டர்ல போறப்ப அதனால ப்ரொடியூஸ் ஆகக்கூடிய மேக்னெட்டிக் எஃபெக்டை 8 ஏரியால பார்க்க போறோம். ஒரு கரண்ட்னால மேக்னெட்டிக் எஃபெக்ட் ப்ரொடியூஸ் ஆகக்கூடிய ஆர்ஸ்டட் எக்ஸ்பெரிமெண்ட்டை சொல்லி ப்ரொடியூஸ் ஆகக்கூடிய மேக்னெட்டிக் ஃபீல்டை மெஷர் பண்ணக்கூடிய 4 ரூல், முதல் 3 ரூல் டைரக்ஷனையும், 4வது ரூல் வந்து மேக்னிடியூடையும், அதுக்கு பிறகு ஒரு ஸ்ட்ரெயிட் ஒயர், ஒரு சர்க்குலர் லூப், ஒரு solenoidல மேக்னெட்டிக் ஃபீல்டு ஏற்படுறதுடைய மேக்னிடியூட் வேல்யூ டைரக்ஷன் கண்டுபிடிக்கப்படும். ரொம்ப சிம்பிள். பார்ட் 1 really deals with Biot-Savart's law, infinite conductor, circular loop, solenoid. ரொம்ப சிம்பிளா போலாம்.
It's Mr. Anderson, and this is AP Physics Essentials Video 32. It's on the magnetic field of a wire. Scientists for years and years and years knew there was some link between magnetism and electricity, but they couldn't find it. There were a lot of clues that pointed in that direction. If you take two magnets, let them go, north goes to south, just like positive goes to negative. If you pull them apart, there is a force between the two, and that force gets greater the closer those two magnets get together. It's just like charges. There's an attraction between the two, and actually Coulomb's law applies to both magnetic fields and magnetic forces and electric fields. What they also knew is that magnetic fields are created and can be measured using a compass. So if you take a bar magnet like this and move a compass around it, you can see that it's lining up with that magnetic field. And so what they wondered is, maybe if we take a compass and move it next to a charged object, as we move it around that charged object, it's going to point towards the charged object, but it simply didn't. And so it didn't seem like charges were producing any kind of a magnetic field. And then a brilliant Danish scientist named Hans Christian Orsted moved the charge. And so what he's got here is a current. So we've got a current, or we know now that it's electrons that are moving, but the conventional current is going to be in this direction. And so what he found is that as the current moved through the wire, it actually deflected a compass. So that particle, that charged particle, has to be moving. And so we could demo this in a science lab. Imagine if we have a wire coming out of a table and we just put a bunch of compasses around it. And so we've got the wire coming out of the table, it's coming towards us, and then we've just lined a bunch of compasses up, but we haven't turned on the current. Watch what happens when we turn on the current in that wire. You can see that we're creating a magnetic field around the wire, and we can measure that and where it is. And so if you have a wire that's a straight wire, so not a curved wire, and it has a current flowing through it, then we're going to have a magnetic field that goes around that wire. And we can measure the magnitude of that magnetic field, and it's really based on two things. The first one is going to be the amount of charge, and so how much current we have that's moving through that wire, and there's a direct relationship between the two. The more flow there is, the more magnitude we're going to have in the magnetic field. And then we have the radius, or the distance from the wire. And so again, this wire is in cross section, and so this would be the radius, or the distance away from that wire. And so there's an inverse relationship from that. The greater the radius is, the smaller that magnetic field is going to be. Now, how do you figure out which way the magnetic field is going to be? Well, the direction is going to be determined by the right-hand rule. And so what you use is your hand again, but the thumb is going to show where the current is moving, and then the curling of your hands like this are going to show you where that magnetic field is. And so in this case, I know the magnetic field is going from the left to the right. I can see that on my diagram right here. And so is the current flowing towards me or away? If I hold my thumb like this, it's coming towards me. So it's coming through the wire at us like that. And so scientists, again, figured out that a magnet is going to generate a magnetic field. And so in this PHET simulation, what I'm doing is moving the compass around the bar magnet. And you can see now the south end of the compass is pointed towards the north end of the bar magnet. But as we move it around to this side, now it's the north end of the compass pointing at the south end. And so if we look at a simple circuit, so what we've got here is a battery and then a wire that loops back. Watch what happens now when we put a compass and just kind of move it around this is just a simple electromagnet. You can see it's not affected by it at all, but once I turn the voltage on, then you can see it's really essentially a magnet. It's a magnetic dipole. And so as we move it around, you can see that compass needle spinning. And so if we turn on the magnetic field, you can see where those field lines are going to be. And I turn the electrons on as well. You can see it's being attracted, or we're creating a magnetic field. Watch what happens if I turn off that current, it goes to zero, you can see that there's no magnetic field anymore. If I move the compass, it's not going to respond. Let's move it in the other direction. You can see now we've got those field lines again. What's going to happen if we add more wires? Well, we're adding more current, and so watch what happens to the electric field. It's getting greater and greater and greater over time. And so here's that right-hand rule. If we've got current moving through a wire, this is conventional current, all you do is just point your thumb in the direction of where that current is moving, and then as your fingers curl around, it's going to show you where that magnetic field is. And so right here we've got current going up, so I'm going to put my thumb up, and so then we have the magnetic field that's turning around like that. Say the current's going in the other direction, magnetic field is going to go in the opposite direction. How do we quantify it? Here's our equation for that magnetic field. It's going to be the magnetic permeability. Remember, that's the ability of a material to support a magnetic field, and this is just of free space. It's going to be 1 essentially. We then have the current, which is going to be how much electrons or how much conventional current is moving through the wire. Then we've got 2 pi over r. So again, if we increase the radius, we're going to decrease that magnetic field. If we increase the current, so since it's on top of this equation, it's going to increase the magnetic field. Now you might recognize this on the bottom. What is 2 pi r? That's going to be the area of a circle. And that's because as we move farther out from that wire, we're going to have a 2 pi r relationship between the amount of current and then the magnetic field. And so another important thing that you should understand is if we have multiple wires that are going right next to each other. So let's say we have a wire and the current is moving from bottom to top. Can you figure out which way the magnetic fields are going to be? Use your thumb, point it in the direction of the current, so you should have your magnetic fields going like that. But let's say we have another wire right next to it, and it also has current going up. Well, what's going on right here is that we're actually having a magnetic field act on those electrons as they're moving through this wire. And so we can figure out the direction in which that force is going to act. And so we're going to use our other right-hand rule. Remember, that's this right-hand rule where we point in the direction of the movement of the particle. We then have our magnetic field be represented with our middle finger, and then the force is going to be your thumb. So it looks like that. So what we've essentially got is the current in this direction. The magnetic field is going to be in that direction, and so we're going to get a force. So again, we're pointing up like that. I got a magnetic field like that, so the force is actually going to go into the middle of those two wires. And likewise, if we put the other magnetic fields of that wire on, then we're going to get a force that is pushing towards the middle. So if you have two wires and the current's moving in the same direction, there's going to be a force pulling those wires together. And so a way to think about that is if the current flows together, then the wires go together. It's going to pull them together. Likewise, if we are going in the opposite direction, if they flow apart, then those wires are going to be moving apart because we're going to get forces that are moving away from that center. And so did you learn to create a representation of a magnetic field around a wire or a set of wires? Again, always use your thumb, and the more current we have, the greater that field is, and the larger that radius is, the smaller that magnetic field is going to be.
இப்போ நம்ம என்ன செஞ்சிருக்கோம்னாக்க ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போச்சுன்னா அதை சுத்தி ஒரு மேக்னெட்டிக் ஃபீல்டு கிரியேட் ஆகுதுன்னு ஆஸ்ட்ரிட் கண்டுபிடிக்கிறார். ஒரு இன்ஃபைனைட் கண்டக்டர்னா அந்த மேக்னெட்டிக் ஃபீல்டோட வேல்யூ என்ன, ஒரு பேரலல் வயர்ஸ்னா ரெண்டுக்கு நடுவில் என்ன அப்படின்றதெல்லாம் ஜென்ரலா இந்த சாப்டர்ல பார்க்க போறோம். அப்போ முதல்ல கான்செப்டுக்கு வரலாம். ஒரு சார்ஜ் இருந்தா ஃபீல்டு இருக்கும், ஆனா அந்த சார்ஜ் இருந்தா சுத்தி இருக்கக்கூடிய ஃபீல்டுக்கு பேரு எலக்ட்ரிக் ஃபீல்டுன்னு பேரு. மேக்னெட்டிக் ஃபீல்டு இருக்குமா அப்படின்னு பார்த்தாக்கா மேக்னெட்டிக் ஃபீல்டு இருக்காது. ஒரு கரண்ட் கேரிங் கண்டக்டரை சுத்தி மேக்னெட்டிக் ஃபீல்டு இல்ல, ஆனா அந்த கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போயிடுச்சுன்னா சுத்தி மேக்னெட்டிக் ஃபீல்ட் இருக்கு அப்படின்னு ஆஸ்டெட் கண்டுபிடிக்கிறார். இந்த ஆஸ்டெடுடைய எக்ஸ்பெரிமெண்ட் என்ன ப்ரூவ் பண்ணுது அப்படின்னாக்க, ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போறப்போ அதுக்கு பக்கத்துல வைக்கக்கூடிய மேக்னெட்டிக் நீடில் வந்து ஒரு மேக்னெட்டிக் ஃபீல்டு அரவுண்ட் இருக்கிறத சென்ஸ் பண்ணுது. கரண்டோட டைரக்ஷன் ரிவர்ஸ் பண்ணா மேக்னெட்டிக் ஃபீல்டோட டைரக்ஷனும் ரிவர்ஸ் ஆகுது. கரண்டோட மேக்னிடியூட் கூட்டுனாக்க இந்த மேக்னெட்டிக் ஃபீல்டோட வேல்யூவும் கூடுறத அவர் கண்டுபிடிச்சார். இந்த ஆஸ்டெட் எக்ஸ்பெரிமெண்ட் என்ன செய்யுது அப்படின்னாக்க, it establishes a current carrying conductor carries a magnetic field around the wire in a perpendicular direction அப்படின்றத ப்ரூவ் பண்ணுது. அப்போ மேக்னெட்டிக் ஃபீல்டுக்கும் எலக்ட்ரிசிட்டிக்கும் உள்ள ரிலேஷன்ஸை ஆஸ்டெட் எக்ஸ்பெரிமெண்ட் கன்ஃபார்ம் பண்ணதுக்கு அப்புறம் 3 விஷயங்களை கன்ஃபார்ம் பண்ண. ஒரு கரண்ட் கேரிங் கண்டக்டருக்கு நேர்கீழ ஒரு காம்பஸ் நீடில வைக்கிறோம். காம்பஸ் நீடில் நார்த் சவுத்தா நிக்குது, ஜியோகிராபிக்கல் நார்த் நோக்கி நிக்குது. அந்த சர்க்யூட்ல கரண்ட் போறப்ப அந்த ஜியோகிராபிக்கல் நார்த்ல இருந்து அதனுடைய பொசிஷனை மாத்திக்குது. அந்த பொசிஷன் என்ன ஆகுதுன்னாக்க, கரண்ட் டைரக்ஷன் மாறுறப்ப மீண்டும் பொசிஷன் மாறுது. கரண்டோட மேக்னிடியூட் கூடுறப்போ அந்த டிஃப்ளெக்ஷனுடைய வேல்யூவும் கூடுறத ஆஸ்டெட் எக்ஸ்பெரிமெண்ட் கன்ஃபார்ம் பண்ணுது. இப்போ ஆஸ்டெட் எக்ஸ்பெரிமெண்டோடைய டீட்டெயில பார்க்கலாம்.
Long back, sometime in the 1800s, it was thought that electricity and magnetism are two completely different topics, that there was no link in between them. But during that time, there was a scientist known as Hans Christian Orsted. Now, Hans Christian Orsted, a Danish chemist and physicist, was responsible for finding this missing link in between electricity and magnetism. So, how did he find it? So one day, Hans Christian Orsted was lecturing his physics class on electricity. Now he noticed that the circuit which he was using to demonstrate electricity exhibited a peculiar behavior. The moment current was flowing through the circuit, there was a slight deflection in a compass needle that was placed on his desk. But the moment Christian Orsted switched the circuit off, or in other words, stopped the supply of current to the circuit, he found that the deflection no longer existed in the compass needle. Now he was intrigued. Hans Christian Orsted knew that the deflection in a compass needle can only be caused by a magnet, because the compass needle itself is a magnetic substance. So he studied further on what exactly was happening. And then he found out that electricity and magnetism are related. Whenever there is a flow of electricity, there will be presence of magnetism. So this was a groundbreaking discovery in that time. And it was because of this discovery that it paved the way for many, many more discoveries in the future years to come. So he was responsible for finding out the missing link between electricity and magnetism. So now let us see how electricity influences a magnetic needle. In this video, we are going to find that when current flows through a conductor, it is able to influence a magnetic needle, and in what way. So notice this video. Now current is not flowing, but as soon as current starts flowing, you will find that there is a deflection in the needle. And the direction of deflection of the needle changes if I keep the wire differently, which means that the direction of current changes, and depending on the direction of current, the direction of deflection of the needle also changes. So now let us see a simple animation to find out in what way or what is the pattern of the magnetic field around a current carrying conductor. The apparatus we have considered is very simple. We have taken a battery, a cardboard with a hole in it, a copper wire that is properly insulated. This will be carrying current, and a switch. Now you will notice that some iron filings are poured on top of the cardboard, and through the hole of the cardboard, the copper wire is passing. Both ends of the copper wire are connected to the battery which you have taken. Now initially, as you can see, the switch is open and no current is flowing. So the iron filings are randomly placed around the copper wire. Even if you tap the cardboard at this point, you will find that the iron filings still remain randomly placed. Now let's see what happens when the switch is closed and current is allowed to flow. The moment the switch is closed, current starts flowing, and you will find that these iron filings arrange themselves in a certain pattern around the copper wire. This is because current is flowing around the copper wire and causing the generation of a certain magnetic field. Now the pattern of the magnetic field or the magnetic field lines can be easily determined from the pattern of the iron filings. If you look closely, you will see that the iron filings have arranged themselves in concentric circles around the copper wire. Now, the direction of magnetic field lines can be easily plotted with the help of a compass needle. Now, when a compass needle is placed at different points, it will be deflected. So, due to this deflection, the red part of the needle will be pointing in different directions, and it is in this way we will be able to find out and map the direction in which the field lines are pointing, and thereby also decide how the magnetic field is oriented around the conductor. So now you might be wondering that it is very inconvenient to find out the pattern of magnetic field lines with the help of such an elaborate experiment. Now there is a simpler way by which we can find out the direction of magnetic field. Now if we hold the current carrying conductor in this way and hold it in the manner as you can see in the picture, such that the direction of current is given by our thumb, then the direction in which the other fingers will be curling the conductor will give us the direction of the magnetic field. And we have found out from the experiment that the magnetic field is in circles around the conductor. So over here, the direction of magnetic field can be easily determined by the right hand thumb rule. Now while you are holding the conductor, make sure to be careful because current will be flowing through the conductor while you determine the direction of magnetic field. So what does the right hand thumb rule state? The right hand thumb rule states that if we hold the current carrying conductor in the right hand, so let's say that this is a current carrying conductor and we have held it in the right hand such that the thumb points in the direction of current. So let's say current is flowing from bottom to top. So the thumb is pointing in the direction of the current. Then the fingers will encircle the wire in the direction of the magnetic field lines. So this means, as you can see, my fingers are encircling the current carrying conductor, and this will be the direction of the magnetic field lines. So let's say current was flowing from top to bottom. So in that case, I need to hold it like this, and the direction of magnetic field lines will be as given by the curl of my fingers. Now you will notice that the right hand thumb rule is so because if you hold it in the left hand and do the same, the direction given by the curl of your fingers will be opposite, and that will be wrong. So this is why the rule is known as the right hand thumb rule, and that is very important to remember when applying it.
இப்போ ஆர்ஸ்டெட் எக்ஸ்பெரிமெண்ட்டும் அதனால ப்ரொடியூஸ் ஆகக்கூடிய மேக்னெட்டிக் ஃபீல்டோட டைரக்ஷன் கண்டுபிடிக்கக்கூடிய ரைட் ஹேண்ட் தம் ரூலும் பார்த்தோம். இப்போ நம்ம என்ன பண்றோம்னாக்க இந்த சர்க்குலர் லூப்ல கரண்ட் போறப்போ அது மேக்னெட்டிக் போலா பிஹேவ் பண்றதை பார்க்கணும்.
We have seen what happens when current is flowing through a straight conductor in our previous lecture. Now let us see what happens in a current carrying conductor with a slight twist. Over here we place the conductor in a way so as to resemble a loop. So let us see what happens in a current carrying loop. Over here we find that the conductor has been placed in the shape of a loop and on a plastic board with two holes in it. Now when there is no current flowing, the iron filings are randomly placed. Now what happens as soon as current starts flowing? Observe closely. The moment current starts flowing in the current carrying loop, a magnetic field will be generated, and the pattern of the magnetic field will be given by the iron filings, as you can see. Over here, the iron filings are no longer randomly generated, but they have arranged themselves in a particular pattern around the current carrying loop. So the schematic of the experiment is shown over here. Now over here we have considered a cardboard on which the current carrying conductor is placed in the shape of a loop. Two holes have been considered through which the conductor passes through the cardboard. Now through the placement of the iron filings on both the sides, we are able to find out the pattern of magnetic field. Now how can we find out in which direction the magnetic field lines are pointed? Now we can do either of two things. We can use the right hand thumb rule. So let's see what happens if I use the right hand thumb rule at this end. Now if I consider the pen as the current carrying conductor, I can see that current is moving in the upward direction. So my thumb will be pointing in the direction of current and my fingers will be encircling the direction of the magnetic field lines. So it will be in this direction or in this direction. So as you can see, the field lines are as obtained. Similarly, if I apply the right hand thumb rule at this point, I will find that current is flowing in the downward direction. So I consider my thumb in the downward direction. So now you will notice that my fingers are encircling in this direction. So this direction gives me the direction of the magnetic field lines. As you can see, this is the direction of the magnetic field lines. Now you might be wondering that this method is quite inefficient because at both the ends you have to apply the thumb rule. There is a chance that you might forget to invert your hand at this end. So in order to make things simpler, there is a different rule to follow. Now let's see what that different rule is. Now when current is flowing through this particular face of the loop, we find that it is flowing in the anti-clockwise direction. Now when it is flowing in the anti-clockwise direction, with the help of a compass needle, we can easily find out the direction of the field lines. We will find that the field lines are coming out from this particular face. That is, at the face from which we see when current flows in the anti-clockwise direction, we will find that the field lines are coming out of it. Now, what have we studied about field lines? We have studied that field lines come out of the north pole of a magnet. So we can say that when current is flowing in the anti-clockwise direction, that loop is the north pole. Or in other words, that face of the loop acts as the north pole. Conversely, if we consider the other face, now with the other face, current will be flowing in the clockwise direction. Now again, if you consider a compass needle being placed at different points to map the direction of the field lines, you will find that the field lines enter this face of the loop. Now what have we studied about field lines? We have studied that field lines enter at the south pole of a magnet. So we can say that that face of the loop where current is flowing in the clockwise direction, that face acts as the south pole of the current carrying loop. Now this entire thing can be visualized in a much simpler manner. When current is flowing in the anti-clockwise direction, consider the letter N. Now when it is flowing in the anti-clockwise direction, consider both ends of N and place arrows so as to indicate the anti-clockwise direction. As you can see, I have already done it for you. Now since this indicates anti-clockwise direction in the letter N, N stands for north. So this represents the north pole. Similarly, where current is flowing in a clockwise direction, consider the letter S. Again, consider both the ends of S and draw two arrows pointing outwards. So as you can see, these two arrows depict the clockwise direction and the letter S stands for south. So this indicates the south pole of the current carrying loop. Now the same polarity which we had looking at a particular face, that polarity can be reversed if we simply reverse the direction of current. Because we have seen that when current flows in an anti-clockwise direction, it is north pole, and in clockwise direction, it is south pole. So let us say that we are standing at and looking at the same face. We are looking at the same face of the loop without changing our position. Now we can get different polarity on the same face if we simply change the direction of current flow. Over here, it is anti-clockwise, thus north. Over here, simply by changing the direction of current flow, we have made it the south pole. Thus, on reversing the direction of current in the loop, we can get opposite polarity at the same face of the loop.
இப்போ ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போச்சுனாக்க ஒரு மேக்னெட்டிக் ஃபீல்ட் அரௌண்ட் கிரியேட் ஆறத ரைட் ஹேண்ட் தம்ப் ரூலை வச்சு அந்த மேக்னெட்டிக் ஃபீல்டோட டைரக்ஷனை பார்த்தோம். அந்த கரண்ட் கேரிங் கண்டக்டர் வந்து ஒரு சர்க்குலர் லூப்பா இருந்ததுன்னா ஆன்டி கிளாக் வைஸ்ல போனா நார்த் போல் மாதிரி பிஹேவ் பண்றதும் கிளாக் வைஸ்ல போனா சவுத் போல் மாதிரி பிஹேவ் பண்றதையும் பார்த்தோம். இப்ப என்ன பண்ண போறோம்னாக்க அந்த சர்க்குலர் ஒயர் ஒரு சொலினாய்டா இருந்தா என்ன ஆகும்?
Take a look at the picture on the screen. Over here you will find that there are many loops over here which have been generated with the help of a single conductor. Now this is a copper wire. Earlier we have studied that how we can twist a copper wire in the shape of a circular loop, and if current flows to this loop, then a certain magnetic field is generated. Now what if in place of a single loop we have multiple loops one after the other? This can be achieved if we continuously twist a conductor in the manner shown. The structure which we obtain is known as a solenoid. So when current flows to the solenoid, a definite magnetic field is generated. So let us see how we can find out the direction of the magnetic field around a solenoid when current flows through it. This simple experiment, in which we use a simple magnetic needle, demonstrates the direction in which magnetic field is pointed around the current carrying solenoid. As you can see, as the needle is placed at different points around the solenoid, the deflection of the needle changes. This indicates that the needle is pointing towards the direction in which the magnetic field lines are pointing. So now let us take a look at another video where we will be able to find out the pattern of the magnetic field lines. In this video you will find that a solenoid has been considered, and the iron filings initially, when there is no current, are randomly placed. Now notice closely what happens when current starts flowing. As you can see at these parts, at the ends of the solenoid, the iron filings come close to one another and they form a definite pattern. You can see that the definite pattern is being pointed out in the video, and the iron filings at each of the holes has formed a definite pattern. And this pattern gives us the pattern in which the magnetic field is present around the current carrying solenoid. So we found out what the pattern of the magnetic field lines are and in which direction they are pointed. So now consider this picture. Let us say I have considered that current is entering from this direction and exiting from that direction. Now let us consider each of these faces separately. When I look at this particular face, I will find that current is flowing in this direction. Now what does this correspond to? If you look at it closely, then this resembles a clockwise rotation. Now if I resemble the clockwise rotation in this manner, I find that it is the letter S. So clearly this is the south pole, because if you recall from our previous discussion on a circular loop, when we have clockwise rotation of current, it implies the south pole. Similarly, if we consider the other face, we will find that current is leaving the face in this manner. So if I have to look at that face from this side, I will find that current is moving in the anti-clockwise direction. Now, what had we studied about anti-clockwise direction of current in a circular loop? We had found that if we consider the letter N and place two arrows at both ends, this indicates anti-clockwise direction. So this is the north pole of the solenoid. And as you can clearly see from the field lines, the magnetic field lines are leaving the north pole, traveling all the way outside the solenoid and entering at the south pole. And inside the solenoid, they are traveling from south to north. So what does a solenoid behave as? Doesn't this behavior of magnetic field lines seem familiar to you? That is right. This solenoid has field line configuration that is very similar to that of a bar magnet. So over here, we have a bar magnet, and over here we have a solenoid. So as you can see, the field lines, that is the magnetic field lines around a solenoid, have a similar direction and orientation as the magnetic field lines of the bar magnet, provided the north and south of the solenoid as well as the bar magnet are facing the same direction. So we have found out that when current is flowing through a solenoid, and if we look at the solenoid from the top, then this is the south pole because current is in the clockwise direction, and this is the north pole because current is in the anti-clockwise direction. So this is how a current carrying solenoid resembles a bar magnet.
இப்போ 3 விஷயங்கள் பார்த்திருக்கோம். ஆர்ஸ்டட் எக்ஸ்பெரிமெண்ட் என்ன ப்ரூவ் பண்ணுச்சுனாக்க ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போனா சுத்தி ஒரு மேக்னெட்டிக் ஃபீல்ட் கிரியேட் ஆகும். அந்த கரண்ட் கேரிங் கண்டக்டர்ல சார்ஜ் ஃப்ளோ ஆகலனாக்க மேக்னெட்டிக் ஃபீல்ட் கிரியேட் ஆகாது. அப்படியே கிரியேட் ஆகக்கூடிய மேக்னெட்டிக் ஃபீல்ட் கரண்ட் டைரக்ஷனை டிபெண்ட் பண்ணிருக்கு, கரண்டோட மேக்னிடியூட டிபெண்ட் பண்ணிருக்குன்னு ஆர்ஸ்டட் ப்ரூவ் பண்ண பிறகு அந்த கரண்ட் கேரிங் கண்டக்டர் சர்க்குலர் லூப்பா இருந்து அதுல ஆன்டி கிளாக் வைஸா போனா அது நார்த் போல் ஆகும், கிளாக் வைஸா போனா அது சவுத் போல் ஆகும். அதுல ஒரு சொலினாய்டு வழியா ஒரு கரண்ட் போச்சுன்னா அது பார் மேக்னெட் ஆகும், பிகவ் ஆகும். அதனுடைய டைரக்ஷனை படிக்கணும்னாக்க ரைட் ஹேண்ட் தம் ரூல் வச்சு அந்த கர்லிங் ஃபிங்கருடைய டைரக்ஷன்ல மேக்னெட்டிக் ஃபீல்ட் இருக்கிறத பார்க்கலாம் அப்படின்னு சொன்னாங்க. அதே சமயம் ஆர்ஸ்டட் எக்ஸ்பெரிமெண்ட்ல இன்னொரு மிக முக்கியமான ஒரு ரூல், ஆம்பியர் ஸ்விம்மிங் ரூல், அதை பார்க்கலாம்.
In this video, we are going to learn Ampere's swimming rule. Ampere's swimming rule gives the direction of deflection of a magnetic needle placed closer to a conductor which is carrying current. So suppose this is the magnetic needle, and this one is the north pole of this needle, and this one is the south pole. And this is the conductor which is carrying current in this direction. So this conductor is carrying current from left to right. Due to that current, this magnetic needle will be deflected. And the direction of deflection is given by Ampere's swimming rule. That means whether this needle will be deflected in this manner or in this manner, it is decided by Ampere's swimming rule. Imagine a person swimming with his face downwards. So this is the swimmer, his face downwards, and he is looking at the needle. And again, suppose that current enters from his feet and leaves from his head. That means here current is flowing from this point to that point. That means current in this conductor is flowing from left to right. According to Ampere's swimming rule, in this situation, its north pole will be deflected towards the left hand side of this person, and the south pole will be deflected towards the right hand side of this.
Maxwell's corkscrew rule. Imagine a right-handed corkscrew lying with its axis coincident with the current-carrying wire. It is now rotated such that it advances in the direction of the current. The direction in which the thumb rotates gives the direction of the magnetic lines of force. In the given figure, the direction of current is towards the right side and the magnetic lines of force are clockwise.
இப்ப இந்த ரெண்டு ரூலையும் தெளிவா பார்க்கலாம். ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போற டைரக்ஷன்ல ஒருத்தன் தலையை வைத்து நீந்துட்டு போனான்னாக்க அதுக்கு நேர் கீழே இருக்கக்கூடிய காம்பஸனுடைய நார்த் போல் வந்து அவனுடைய இடதுகை புறமா திரும்பும் அப்படின்றது ஆம்பியர் ஸ்விம்மிங் ரூல். மேக்ஸ்வெல்லுடைய ரைட் ஹேண்ட் கார்ஸ் ரூல் என்ன சொல்லுதுனாக்க ஒரு கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் டைரக்ஷன்ல ஸ்க்ரூ நகரணும்னாக்க எந்த திசையில சுத்தணுமோ அந்த திசையில மேக்னெட்டிக் ஃபீல்ட் இருக்குன்னு சொல்லுது. ஐன்ற கரண்ட் மேல் நோக்கி இருக்கு, அந்த டைரக்ஷன்ல ஸ்க்ரூ சுத்தணும்னாக்க கிளாக் வைஸாகவும், கீழே வந்ததுனாக்க ஆன்டி கிளாக் வைஸா இருக்கிறத நம்ம ப்ரூவ் பண்ணிக்கிறோம். இப்போ 3 ரூல் பார்த்தோம். ரைட் ஹேண்ட் கர்லிங் ரூல், ஆம்பியர் ஸ்விம்மிங் ரூல், மேக்ஸ்வெல் ரூல், கிளாக் ரூல். இது எல்லாம் டைரக்ஷனை மட்டும்தான் சொல்லுது. இப்போ ஒரு ரூல் சொல்ல போறோம். அந்த ரூலுக்கு பேரு பயட் சபர்ட்ஸ் லான்னு பேர். இந்த ரூல் என்ன சொல்லுதுன்னாக்க ஒரு கரண்ட் கேரிங் கண்டக்டர்ல டிஎல்ன்ற லென்த்ல ஐன்ற கரண்ட் போய் அந்த கரண்ட் கேரிங் கண்டக்டர்ல இருந்து ஒரு பாயிண்ட் ஆஃப் ஆப்சர்வேஷன் ஆன் த டிஸ்டன்ஸ்ல தீட்டான்ற ஆங்கிள் இருந்ததுன்னா அந்த கரண்ட் கேரிங் கண்டக்டர்ல P is the point of observation, DL is the length of the segment, I is the current flowing through, which is making an angle theta, and if R is the distance of the point of observation from the current carrying conductor, magnetic field produced are the current க்கு directly proportional இருக்கும், DL க்கு directly proportional இருக்கும், sin theta க்கு directly proportional இருக்கும், R square க்கு inversely proportional இருக்கும்னு சொல்றது பயட் சபர்ட்ஸ் லா. ப்ரொபோர்ஷனாலிட்டியை நீக்கிட்டா அங்க ஒரு கான்ஸ்டன்ட் வருது, அதோட வேல்யூ μ0/4π. அப்போ dB is equal to μ0/4π ஐடியல் sin θ/r² சொல்றது பயட் சபர்ட்ஸ் லா. இது வெக்டோரியல் ஃபார்ம்லயும் சொல்லலாம். இந்த கரண்ட் கேரிங் கண்டக்டர்ல கரண்ட் போறதுனால ப்ரொடியூஸ் ஆகக்கூடிய மேக்னெட்டிக் ஃபீல்ட் எய்தர் டுவர்ட்ஸ் அஸ், அது எமர்ஜிங்கா இருக்கும் அல்லது என்டரிங்கா இருக்கும். அது டிஎல் கிராஸ் ஆர் டைரக்ஷன்ல இருக்கும். இப்போ இந்த பயட் சபர்ட்ஸ் லாவை 3 வடிவத்துல பார்க்கலாம். dB is equal to μ0/4π ஐடியல் sin θ/r²ல அந்த sin θ காம்பனன்ட் இருக்கிறதுனால ஐடியல் இன்டு ஆர் பொசிஷன் வெக்டர் அப்படின்றத போட்டோம்னாக்க டிஎல் அப்படின்ற கரண்ட் எலிமெண்ட் பொசிஷனல் வெக்டர் அந்த பாயிண்ட் ஆஃப் அப்சர்வேஷன் பொசிஷன் வெக்டர் ரெண்டுத்தையும் கனெக்ட் பண்ணி டிஎல் கிராஸ் ஆர் அப்படின்னு எழுதினோம்னாக்க வெக்டோரியல் நோட்டேஷனா மாறிடும். இந்த ஐடியல் அப்படின்றதுல ஐன்றது கரண்ட், I/A இஸ் கால்டு J கரண்ட் டென்சிட்டி. மேலே கீழேயும் டிஎல் ஆல மல்டிப்ளை பண்ணுங்க. ஐடியல் பை ஏடிஎல், ஏரியாவையும் லெங்க்தையும் மல்டிப்ளை பண்ணா அது டிபின்ற ஒரு வால்யூமை கொடுக்கும். அப்ப ஐடியலுக்கு பதிலா JDB போடலாம். அப்போ μ0/4π ஐடியல் கிராஸ் ஆருக்கு பதிலா ஐடிஎல்லுக்கு பதிலா JDB போட்டாக்க அடுத்த ரிலேஷன் வந்துருது, J கிராஸ் ஆர் வந்துருது. இப்போ மீண்டும் ஐடிஎல் ஐ எடுத்துட்டு ஐக்கு பதிலா dQ/dt போட்டு dL/dtக்கு பதிலா V போட்டோம்னாக்க QV ஆயிடுது. இப்போ Q வந்து ஸ்கேலரா இருக்கிறதுனால V கிராஸ் ஆர் போட்டுக்கிறோம். அப்போ DL கிராஸ் ஆர், J கிராஸ் ஆர், V கிராஸ் ஆர் என்ற 3 வடிவங்களை பயட் சபர்ட்ஸ் லா பெறுது. இந்த பயட் சபர்ட்ஸ் லாவும் கூலும்ப்ஸ் இன்வெர்ஸ் ஸ்கொயர் லாவும் ஒன்னோட ஒண்ணா இருக்கு. அங்க கரண்ட் எலிமெண்ட் The current element produces the magnetic field. Inga point charges produces an electric field. Magnetic field varies as the inverse square of the distance from the current element. அதே மாதிரி அங்க point charge. Current element லந்து point of observation உள்ள distanceக்கு inverse square law obey ஆகுது. இங்கே inverse square law obey ஆகுது. But point charge வந்து create பண்றது ரேடியலா இருக்கு. Axial lineல இருக்கு. இங்க perpendicular lineல இருக்கு. இதுதான் மிகப்பெரிய ஒரு வித்தியாசம். அப்புறம் the Biot-Savart's law for the magnetic field has a certain similarity as well as the differences in the Coulomb's inverse square law. Some of these are, both the things are long range. Since both depends upon the inverse square of the distance from the source to the point of interest. But the principle of superposition applies to both the fields. ஆனா இங்க என்ன சொல்றோம்னாக்க magnetic field is linear. அதாவது note that the magnetic field is linear in the case of ideal, just as the electrostatic field is linear in its source. அப்போ ஐடியல்ன்றது லீனியரா இருந்தா இதுவும் லீனியரா இருக்கு, சார்ஜ் லீனியரா இருக்கப்ப லீனியரா இருக்கிற மாதிரி சிம்பிளா புரிஞ்சுக்கிட்டோம்னாக்க electrostatic field produced by a scalar source called charge, magnetic field is produced by a vector source. Major differences என்னன்னாக்க இது axial lineல இருக்கும், radial lineல இருக்கும், இது equatorial lineல இருக்கும் magnetic field. அதான் மிகப்பெரிய வித்தியாசம். இதை கம்பேர் பண்ணோம் அப்படின்னாக்க the electrostatic field is along the displacement vector. The electrostatic field is along the displacement vector joining the source and the field point. But whereas the magnetic field is perpendicular to the plane containing the displacement vector or under current element. அங்க அது along the line joining இருக்கு, இங்க perpendicular. There is an angle dependence in the Biot-Savart law which is not present in the electrostatic case. Axial lineல இருக்கிறதுனால magnetic field வந்து angle dependence இருக்கு, electrostaticல கிடையாது. The magnetic field at any point in the direction of dl is zero. The magnetic field at any point in the direction of dl is zero. அதாவது theta is equal to 0 நாக்க sin theta is equal to 0, so for dB is equal to 0. எலக்ட்ரோஸ்டாட்டிக்ஸ்ல ஆங்கிள் காம்பனன்ட் கிடையாது, Biot-Savart's lawல ஆங்கிள் காம்பனன்ட் இருக்கு. அங்க இருக்கக்கூடிய ஆக்சியல் லைன்ல எலக்ட்ரிக் ஃபீல்ட் இருக்கு, இங்க இருக்கக்கூடிய ஆக்சியல் லைன்ல மேக்னெட்டிக் ஃபீல்டோட வேல்யூ 0. இங்க எப்சிலான் நாட் அப்படின்றது எலக்ட்ரோஸ்டாட்டிக்ஸ்லயும் மியூ நாட்ன்றது மேக்னடிசத்துலயும் கிரியேட் ஆகக்கூடியதுல இது ரெண்டையும் மல்டிப்ளை பண்ணா 1/c² ஒரு வேல்யூ வருது. இட்ஸ் a very very interesting factor. C is called the velocity of light. சரியா? இப்போ Biot-Savart's lawவை இன்னும் கொஞ்சம் விரிவா பார்க்கலாம்.
Okay, now I'd like to tell you about the law of Biot-Savart. I don't think you pronounce the T actually. It's the law of Biot-Savart, or the magnetic field due to a current element. Okay, calculating the magnetic field due to a current element, you would use the law of Biot-Savart. Okay, so a current element. First of all, what is a current element? This is just one segment of a wire. Imagine that there's a whole bunch of wire going this way. So you got the whole wire going that way. But we're going to just look at one segment. And the segment we're going to have is going to be infinitesimally small. So we're going to call that length dl. Now I had to draw it big so that you could see it. But it's really going to be, when we do the math for this, we're going to assume that dl is really tiny, infinitesimally tiny. Now the current is heading this way, and let's just say it's heading straight down the way. And the current is I. Turns out that if you want to figure out the magnetic field due to this, just to this little current element, well, if you want to know it here, then you go from the center of your dl, you draw a vector r, and let's see, which way is it going to be heading? It's going to be heading, the field is going to be heading straight up. Yeah, that's right, straight up. And let's call this angle theta. The angle between the direction of dl. dl, we're going to call it, that's going to be a vector. It's going to be pointing in the same direction as I. So I need to sneak a vector sign in there for dl. Okay. Now to get the field just due to this little dl is really tiny. And so to remind ourselves that this is a field not for the whole wire, But just for DL, I'm going to put the field there. It's not a big field, it's a little field. It's dB field. Okay, so the dB, the little field, the very tiny, tiny field due to this little dl, is going to equal, it's going to look very similar to the equation from the last video. It's going to be mu naught over 4 pi. Remember, this whole thing equals 1 times 10 to the negative 7th. And the units on that are Teslas, meters over amps. So I'll write that here. Mu naught over 4 pi. That's going to be 1 times 10 to the negative 7th. And the units on that is Teslas, meters over amps. And you'll see why that has to be Teslas, meters over amps in a little bit. A different video, actually. Okay, so this is mu naught over 4 pi. And then times I times dl cross r, or we can say I dl sine of theta all over r squared. So this looks a lot like qv sine of theta over r squared, except we're going to have the I times dl times the sine of theta over r squared. There's a cross product in here. You could say it's I dl, that vector, cross r, and then you would have an r cubed down here. Another way to do that also is to use a unit vector, and I won't go into that, but maybe your book has I dl cross a unit vector, and the unit vector has a magnitude of 1, so that's why that's still just r squared down here. Okay, well, in any case, the magnetic field due to this current element is going to be just a constant times how big the current is times dl times the sine of theta, the angle that it makes, all over r squared, r being the distance from the center of the dl to where you want to find the field. Okay, so let me show you how this works for a line, a long wire, a chart, the magnetic field due to a long line of current going. Let's have the wire be going this way. So here's a wire, and it's infinitely long both ways. And I'm going to put a coordinate system on here. There we are. And let's say we want to know the field due to this wire. And let's say this distance from here to there is a distance a away from the wire. And let's say the current is heading up. So the I is up. That's the I. And right now I know that the field, the direction of the field right there is going to be into the page. So if I put a compass right here, if I put a compass there, it's going to point down. If I put a compass on this side, it will point up. Okay, but I'd like to know what the field is there, the strength of the field. Okay, so I'm going to make a little dl, and I'm going to find the field due to that little dl. That field due to that little dl is this. I'm going to make a little dl. That's a little arrow I drew there. It's hey, I know I call it dl, but because I'm in the y direction, how about I call that dy? And this is down here, a distance of y down here. So it's down a distance y from the origin, and it's the thickness of this little bit of wire is dy, or the height of that wire is dy. Okay, well, the r is this vector. And so to get the field due to that, it's going to be mu naught over 4 pi, just a constant. And now I'm going to do I times dl, but I changed the dl to dy since it's in the y direction. I times dy times the sine of theta all over the r squared. Okay, now I'm going to add up then for every circuit, for every current element, that each one of these has some effect on the field there. And so what I'm going to do is I'm going to just add them all up with an integral. But there's a problem when I do that. When I go to integrate this, do you see how my differential is dy? But what else is changing? Depending on where I go, the theta changes. So if I'm right here, theta is 90 degrees. But if I'm down here, theta is smaller. So theta is changing. And so is r. R, how far away this is from the point I want, is changing. So I have a variable in r, a variable in theta, and my differentials in dy. So this is a problem. Okay, well, what we do is we're just going to put everything in terms of y. So I can put theta in terms of y, and I can put r squared in terms of y. It turns out that before I integrate, I'm going to do this. So bring this over. Use I. I is just a constant. It's a number that would be 4 amps or 1 amp or what have you. I'll have a dy there. But to get r squared, if I'd like to get r squared in terms of y, you see if this is r, that I can put that in terms of y with the Pythagorean theorem. Turns out that r is going to be equal to the square root of y squared plus a squared. And when I square that, I get this. So I just get that. And the theta, the sine of theta, is the opposite side over the adjacent side, or the hypotenuse. So sine of theta is the opposite side, A, over the hypotenuse. And the hypotenuse is r again. So it's going to be r squared plus a squared. This time I have to square root it. There's no square root here because remember we square that r. Okay, well, it turns out then that I can combine these a little bit. And so dB is equal to mu naught over 4 pi. And then I'm going to have I dy a just being a constant. And then this can combine to y squared plus a squared to the 3/2 power. Okay, now I don't want just the field just due to this current element. So to get the field due to all of them, I'm going to sum up with an integral. I'm going to pull out all the constants, mu naught I a over 4 pi. And I'm going to sum up the dy over y squared plus a squared to the 3/2 power. And I'm going to start at in y equals negative infinity, and I'm not going to stop summing those to y equals infinity. Okay, when you do that integral, I'll tell you what you get in the next video. So when you do this integral, I'll tell you what you get. Okay, I'll see you. Okay, now I'd like to tell you about the law of Biot-Savart. Okay, this is the law of Biot-Savart, part 2. So we're on part 2, and so we finished that last one, and I had this integral, and it got pretty complex. In that I have all these constants in front of this integral, mu naught I a over 4 pi, and I'm trying to take the integral of dy over y squared plus a squared to the 3/2 power. And I'm integrating from y equals negative infinity, because our wire goes way down there, all the way to y equals positive infinity. But you know, when you go way down there or way up there, they hardly add anything to the field. They don't, because r is so huge. When you're way down there, the r is so huge that and the theta is so small that you hardly add anything. Well, I'm going to tell you, if you were kind of looking forward to seeing me solve this integral, I'm not going to do that. But if you went to a table of integrals, or if you plugged in this integral into your calculator, it could tell you what the answer to this is. The answer to this turns out just normal integration by substitution doesn't get this done, but maybe a little trigonometric substitution would. And you get this. You get mu naught I over 2 pi a. Ain't that nice how it simplifies to mu naught I over 2 pi a, where a is just the distance that you are if you drew a line from the point that you want to a line that was perpendicular to the wire, that's A. Okay, so there you have it. So it's mu naught I over 2 pi A. Now, next, I want to show you how this gets used with a different situation. Sometimes they have problems with the law of Biot that are much more simple to do than the last one. And so this is a very typical problem in AP Physics or in just introductory physics. Excuse me. So you'll see why it's a lot easier to do. You have a wire that is moving along like this. The current's moving along, and then it goes in this semicircular loop, and then it continues on its way. And they want to know the field right at this point. So the question is, what is B right there? Okay, let's figure out what direction it's going, first of all, the B. Well, it turns out that, you see this part of the wire, it doesn't put any field right here. Nor does this wire. Because if you think about it, if this is your DL, and this is your DR, do you see the angle between DL and DR is 0? And so when you use this equation, I dl sine of theta all over r squared, the angle theta is the angle between DL and R. And so that's going to be 0 degrees, and the sine of 0 degrees is 0. So there is no magnetic field from this part of the wire or this part of the wire. However, this part of the wire there is a magnetic field, but you get a lot of nice cancellations. Okay, for one, take a look. If this is my DL, the DL is going tangential there, and this is my R. Do you see what the angle is between DL and R? It's right. It's a right angle. That's 90 degrees. The whole time, no matter which part you're on, like if you're here or up here, DL and R are always at a right angle. So you can make this sine of, this is really the sine of 90, which is just 1 the whole time. Okay. Another thing about this is that R, this vector R, never changes in size. It's always the same size, and so that you can treat as a constant too. For this path, it's always a constant A. And so let's see what we get when we do this. We get dB is equal to, let's pull out all the constants. Mu naught I is a constant. Sine of theta, I'll just call that 1. And then I got 4 pi, and our R happens to be A, and it's A squared. And then I'm going to sum up all the DLs. But when I add up all the DLs, if that's the only thing in my integral, what are all these DLs when I add them all up, these little distances, DLs? When I get done summing all those DLs, I'm thinking that what you get is the half of the circumference of a circle. So when you sum all those up, what you get is mu naught I all over 4 pi A squared. And then this integral is going to give me pi times A. Not 2 pi A, because this is just a half a circle, so it's just pi times A. So we can cancel out a pi and an A. So the field, oh, I'm sorry, I made a mistake here. When you integrate this, you get rid of, when you get the whole B. It's not just, this is just for one little B. But once you integrate it, then this becomes the total B. And so the total B is going to be equal to mu naught I all over 4A. How nice. How nice is that? It's mu naught I over 4A. Okay. So that's how you use the law of Biot. There's other things that you can do as well to make a fairly difficult problem become much easier. For instance, what if this went like this? What if instead of doing this, it came in like this? We get a white background. So here are 2 wires. Those are the 2 wires coming in, and then it circles around like this, and then it goes out that way. Well, you see this DL? It's always at a right angle to R. And so it's pretty much the same as the last problem. You can pull everything out of your integral. And when you sum up all these DLs, it turns into 2 pi A. So that's the only difference. Okay? So that's how you can apply the law of Biot-Savart in some simple situations. Thanks. Bye.
இப்போ Biot-Savart's law இருந்து இன்ஃபைனைட் கண்டக்டருக்கு அவருடைய ஒரு மெத்தட்ல டிரைவ் பண்றதை பார்த்தோம். ஃபார்முலால நெட் ரிசல்ட் அப்படிதான் வருதே ஒழிய, ஆனா ப்ராப்ளங்கள் போடுறப்போ அது சர்க்குலர் வயரா செமி சர்க்குலர் வயரான்றதெல்லாம் இஷ்யூஸ் இருக்கு. அது மட்டும் இல்லாம நம்ம என்ன பண்றோம்னாக்க சர்க்குலர் லூப் ஒண்ணுல அது எப்படி இருக்கு அப்படின்றத அவங்க எப்படி டிரைவ் பண்றாங்கன்னு பார்க்கலாம்.
Okay, this video is on the magnetic field on the axis of a circular hoop. Okay, so what about this magnetic field on the axis of a circular hoop? Here's a circular hoop. It's got some current in it. Let's say the current is going around like this. That's the I through it. It's going around like this. This part is closer to you than this part. And they want to know what the magnetic field is, say, right here. Okay, so let's call the radius of the hoop R. So the radius from there to here is going to be capital R. Okay, so what we do is we use the law of Biot-Savart. We're going to break this into, let's just analyze one little segment of this. A little segment DL. And DL is coming out this way. That's the direction of DL. Coming out that way. It's actually pointed in the negative y direction right now. At the top, it's pointing in the negative y direction. And here I'm going to draw a line that goes straight down to this point. Okay, let's call this distance x. And I'm going to tell you that the field, just due to that dl, if you take your right hand and you put it in the direction of the current, then, and you curl your fingers, then it's going to be a circular field just due to dl, and it's going to point this way. It's going to be at a right angle to this, so it's going to be like that. Okay, now that's going to be called, we're going to call that the magnetic field just due to that dl, so that's going to be a dB. Now, let's look and see what does the magnetic field do to this dl down here. This dl is heading this way. It's heading in the positive y direction. It's heading that way. And if I take my fingers and curl them like that, then right here, if I were to draw a vector from here to there. Now those look like they're in the same direction, but the dl there is actually perpendicular to this vector. And the magnetic field for this is going to be diagonally downward, again at a right angle. So this is going to be at a right angle, and so is this one. This will be at a right angle too. Okay. Now the magnetic field then, due to those dLs, if we wanted to figure out the magnetic field just due to the one, we'll use the law of Biot-Savart. dB is equal to mu naught times I. We're going to say that we know the I in this ring. So it's mu naught I times dl times the sine of theta. This is the law of Biot-Savart over 4 pi times this distance squared. Now what should we call that? Let's call that little r squared. Okay, this distance we're going to call little r. That's this distance as well. Okay, well, you see, that's the magnetic field from this little dl up here, but here's the problem. Each one of these little dl's, as you go around, they each point in a completely different direction. So this one points that way, the dl from this points that way, or excuse me, the db from this points that way. So they're all, it kind of forms a TP around here if you think about it. And for every one up here, there's one down here that's going to cancel. So like this part's db, say y in this case, or z rather, that's dbz. Yeah, dbz is going to cancel with this one, that dbz. So those are going to cancel, and what you're going to be left with is just, for these two at least, is you're going to just be left with the x components. In fact, you're going to be left with the x components for all of them. Okay, so I'm going to say that you only use the x component. Well, the x component is going to be times the cosine of that angle, theta. So that would be, if I wanted just the x component, then I could really add them. And that's going to be times the cosine of theta. That's what gets me where this is theta. Okay, well, what I'm going to do now is I'm going to sum those up with an integral. So I have to sum these up. So when I sum these up, I get dbx. I guess I should let you see this equation. There it is. dbx is equal to mu naught I dl. Now that's sine of theta. This is the angle between dl and r. And so that sine of theta is that theta there. That's a different theta than this one. So I'm going to call this theta 1 and theta 2. And theta 1 is the angle between dl and r. And I'm going to argue that that's a 90-degree angle. So you don't, the sine of 90 is just 1. So that's going to just turn into 1. It's always at a right angle. It's tough to see in my drawing, but dl, that little vector, is always perpendicular to r. Okay, now so I'm getting rid of that, and then I got the cosine of theta. But you know, theta doesn't change in here. No matter which dl I'm at, theta, this theta is always the same angle, same size of angle at least. And so it's mu naught I dl cosine of theta. And then that's going to be over 4 pi and then r squared. Okay, to get the entire magnetic field then, the entire magnetic field is just going to be summing these all up with an integral. Okay, but you can pull out anything that's not you can pull out any constants, and so the mu naught's constant, I is a constant, the theta is a constant, so is the r a constant. So when I pull those all out, I'm just left with mu naught I cosine of theta all over 4 pi r squared, and you're summing up all the dl's. Well, to sum up all the dl's is just going to, when you sum all these little guys up around the circle, that's going to just give you 2 pi capital R. So that's going to be, the b around there is going to equal mu naught I cosine of theta times 2 pi capital R all over 4 pi r squared. All right, now we would like to, what we're going to do, we're done, but I want to change that theta into terms with little r's and big r's and stuff in it. Okay, so let's take a look at theta here. Okay, remember this is a right angle. The angle that B makes with the r vector, it's always going to be a right angle. And this straight line is 180 degrees. This is 180 degrees from here to there. And so if that's theta and that's a right angle, then this has to be the complement of theta. This is 90 minus theta. And if this angle is 90 minus theta, and that's a right angle, then this is theta. We're back to theta. And so we can say that the cosine of theta, if I want to substitute in, the cosine of theta is the adjacent side divided by the hypotenuse. So the cosine of theta is the adjacent side, that would be capital R, divided by the hypotenuse, little r. So I'm going to put that in for that. So as it turns out, that B, almost done here, B is going to equal mu naught I 2 pi r over 4 pi r squared, and the cosine of theta we said was capital R over little r. Okay, now I'm just going to sub in then for r, for lowercase r. Isn't lowercase r this guy? Isn't it r squared plus x squared? So it's, well, the square root of r squared plus x squared. So I'll sub in for that, and then I'll be done. So sub that in, and that's it. Thanks. Bye.
ரொம்ப ஈஸியா கரண்ட் லூப் சர்க்குலர் கரண்ட் லூப்புக்கு மிக காம்ப்ளிகேட்டடா இல்லாம ஒரு ஃபார்முலா டெரைவ் பண்றத
This video is on the magnetic field on the axis.
இப்போ நம்ம என்ன பண்ணிருக்கோம் அப்படின்னாக்கா ஒரு சர்க்குலர் லூப்ல ஆக்சியல் லைன்ல மேக்னெட்டிக் ஃபீல்டுக்கான ஃபார்முலா டெரைவ் பண்ணிருக்கோம். ரெண்டும் ஒண்ணா தானே வருது. ஸோ சென்ட்ரல் பாயிண்ட்ல என்ன அதுக்கு என்னன்றதை பார்த்தோம். இதான் இதுல இருக்கக்கூடிய மேக்ஸிமம் டெரிவேட்டிவ் பார்ட். இப்போ நம்ம என்ன பண்ண போறோம்னா இதை யூஸ் பண்ணி ப்ராப்ளம் எப்படி போடுறதுன்ற பத்தி அடுத்த எபிசோட்ல பார்க்கலாம்.